Hi everyone, welcome back. In this particular video, we're going to talk about deactivating groups, which behave as meta-directing groups. And what that means is when you have a deactivating group on an aromatic compound, it sends the incoming electrophile to the meta position. We'll use the nitration of nitrobenzene as an example to understand this phenomenon. So if we start with nitrobenzene, and we do a nitration on this molecule, we can expect three possible products, which would be the ortho-dinitrobenzene, the meta-dinitrobenzene, and the para-dinitrobenzene. When you look at the product distribution, what we see is that the meta-dinitrobenzene is the major product under these conditions. So nitrobenzene is about 100,000 times less reactive than benzene in this particular reaction. So that gives us a sense of how deactivating the nitro group is. So let's try to understand why that is so. Why is the nitro group such a strong deactivating group? So we can cite two reasons for this effect here. One is an inductive effect. So if we consider nitrobenzene, and I'm going to draw the Lewis structure of the nitro group, what we can see is that there is an inductive effect at play here because the nitrogen here is electronegative than carbons, and additionally the nitrogen has a formal charge, a positive formal charge, and it's bonded to two oxygens. So overall, inductively, the nitro group is electron withdrawing. So the nitro group is electron withdrawing due to inductive effects, and which means it's going to make the aromatic ring. It's going to make the aromatic ring electron deficient. It's going to make the ring electron deficient. Now, the other factor that's usually at play is resonance. So we can consider resonance in nitrobenzene. So if we start with the Lewis structure for nitrobenzene, what we can do is we can start pushing electron pairs from the pi bond here. And in this particular case, the pi bond is going to move outside the ring. And simultaneously, we can push this pi bond over. So the next resonance form is going to look like this, where we have a double bond to the nitrogen and the ring. The oxygens, both of them have a negative charge, and the nitrogen has a positive charge over there. Double bond here and double bond here. And now we can do further resonance within the ring. So the next resonance form that we're going to get is going to have a double bond N, O minus, form a positive charge over there. 3 electron pairs on each of those oxygen atoms, double bond here, positive charge here, and double bond over there. And further resonance form can be written using the other pi bond that's available. And that is going to give us additional resonance form where we have O minus, form a positive charge. Lone pair on the oxygens, double bond here, and a positive charge over there. And finally, we can bring this pi bond back to write the last resonance form, and we can use the lone pair on this oxygen. We could have used the lone pair on any of those oxygen atoms, it doesn't matter. But the last resonance form that we got brings us back to an arrangement which was there in the first structure here, where the ring is aromatic again, and we've got the nitro group. So now if we survey all of these resonance forms that are possible for nitrobenzene, what we see is that these resonance forms, they land a positive charge on the ring, some of the carbon atoms in the ring. So that means the ring carbon atoms are electron deficient. So carbons in the ring are electron deficient, and which basically means that the ring is deactivated. So in particular case of the nitrobenzene, what we are seeing here is that both the inductive effect and the resonance effect, they are deactivating the ring. They're both withdrawing electron density from the ring or making the ring more electron deficient. And so that explains why the nitro group is such a strong deactivating group, that it undergoes the reaction about 100,000 times slower than benzene, the parent molecule. In order to understand the product distribution that we see in the nitration of nitrobenzene, where the meta product is the favored product or the major product, we will have to look at the mechanism of the reaction, and we'll have to specifically look at the mechanism that leads to the formation of each of these products. So let's get started with the ortho product here. So if we start with the ortho product, we've got the nitrobenzene aromatic compound, and again our electrophile here is the nitroneamine. So that is a constant as long as we are talking about a nitration reaction. So again, since we are working on the mechanism here, we are going to use, and we are working on the mechanism for the formation of the ortho product, we're going to use a pi bond that involves the ortho carbon. So the sigma complex that's going to result from this initial attack is going to have the H and the nitro group here and the carbocation on the meta carbon. So we've made the sigma complex here. And now this sigma complex is resonance stabilized. So we can move around the pi bonds in the ring to do resonance here. So we get the carbocation here, double bond here, H and NO2 over there, and double bond here. Pi bond moves. NO2, positive charge, double bond, H and NO2. So those would be all the resonance forms for the ortho attack here. Let's write similar resonance forms for the formation of the meta product. So for the meta product, again, we start with nitrobenzene. And the ring is going to do a nucleophilic attack on the nitroneamine, which is the electrophile. And this time we're going to use a pi bond here. Again, this pi bond, because that pi bond involves the meta carbon and the ortho carbon. So we can use that same pi bond. And this time we're going to attach the nitro group to the meta carbon. The nitro group here, the positive charge ends over there, double bond and double bond. And again, the sigma complex is resonance stabilized. So we can draw resonance forms for the sigma complexes here. Double bond, H and nitro. And we've got positive charge here, NO2, H, and NO2, double bond, and positive charge. So those would be all the resonance forms for the formation of the meta product. Resonance forms of the sigma complex for the formation of the meta product. And finally, we can write the resonance forms that lead to the formation of the para product. So we start with nitrobenzene again. attacks the nitronium ion. And since we are working on a para product here, we're going to use a pi bond that involves the para carbon. So that bond can go and attack the nitro group. It's going to give us a sigma complex, H and NO2. We have double bond here, NO2 over here, double bond, and positive charge over here. And this sigma complex is again resonance stabilized. NO2, double bond here, H and NO2, and a positive charge over there. And then we can use the other pi bond to put down the final resonance form here. Go double bond here, H and NO2, and a positive charge over there. So those would be all the resonance forms for the formation of the product, the para product. Now, the reason why the meta product is the major product has to be in these resonance forms. These resonance forms should be able to tell us why the para product is favored. And when we survey all of these resonance forms, notice that for the formation of the ortho product, there is one resonance form where the carbocation lands on a carbon that's next to the nitro group, which is an electron withdrawing group, a strongly electron withdrawing group. And the same is true for the formation of the para product. The carbocation lands on a carbon which is next to the nitro group. So the formation of these carbocation intermediates in the resonance, this is going to be unstable. And this is also unstable. Now, when you look at the resonance forms for the sigma complex that leads to the formation of the meta product, what you notice is that in each of these resonance forms, the carbocation avoids that carbon which bears the nitro group. It is never formed on that carbon, which means it is not as destabilized as the ortho and the para sigma complexes. So that destabilization that happens for the ortho and the para complexes, that explains why the meta product is the major product under these conditions. So the meta is not stabilized, but it is not destabilized like the ortho and the para sigma complexes. And that explains why the meta is the major product here. I hope you find this video helpful. Bye.